Begin by understanding the computational costs associated with large language models. Computational cost refers to the resources required for training and running LLMs, and that will include things like GPU and CPU usage, memory allocation, and energy consumption. These resources are essential, but also represent a significant challenge when scaling or deploying these models. For example, training a state-of-the-art LLM can require weeks or months of computation on hundreds of GPUs, consuming vast amounts of energy. This makes computational cost a key factor in determining the feasibility of developing or deploying LLMs. For many organizations, this cost can be a barrier, particularly when resources are limited or when environmental sustainability is a concern. So let's look at the key elements of computational costs in LLMs. Larger LLMs require massive amounts of computational power. This includes not only the resources for training, but also for inference. Running these models at scale, after you have them trained and you're out in production, often involves specialized hardware like GPUs or TPUs. Trade-offs between performance and cost. For every gain in accuracy or capability, there's a corresponding increase in cost. These trade-offs are critical for organizations to evaluate when selecting or designing an LLM. The impact on environmental sustainability. Computational costs aren't just financial, they also have an environmental footprint. The energy consumption associated with training and running LLMs has sparked conversations about green AI and the importance of optimizing resource usage to reduce transmissions. Some key factors that influence the computational costs of LLMs are model size. Of course, larger models require more resources to train and run, more memory, extensive computation, and this is going to directly impact costs. Training data sets. The size and complexity of the training data sets is going to affect computational costs. Larger data sets require more time and resources to process, adding to the overall expense. Hardware requirements. So specialized hardwares like GPUs and TPUs are essential for training large models efficiently. And fine-tuning and optimization. So models that are not optimized may incur higher computational costs during training and inference. So managing these costs are critical for making LLMs accessible and sustainable. So here are some effective cost reduction strategies. Model distillation. This involves creating smaller models that retain the knowledge of larger models. These smaller versions are faster and cheaper to run while maintaining good performance. Transfer learning. So by using pre-trained models and fine-tuning them for specific tasks, organizations can reduce the time and resources needed for training. Efficient training frameworks. So leveraging optimized frameworks and libraries can significantly lower computational requirements. And batch size and learning rate adjustments. So fine-tuning these parameters help optimize training, reducing the number of iterations and overall costs. One of the biggest trade-offs in LLM development is between cost and accuracy. Larger models are more accurate, but require high computational costs. Smaller models are less costly, but may have reduced performance. So while these models are efficient and affordable, they often lack the depth of understanding and contextual reasoning found in larger models. So how can we balance the cost and performance? Infrastructure requirements. High performance hardware such as GPUs and TPUs are essential for running LLMs effectively. The availability and cost of this infrastructure can greatly impact overall project feasibility. There's also ongoing costs after deployment for hosting and maintaining the model, particularly for cloud-based deployments. Larger models generally incur higher deployment costs due to their resource demands. And energy consumption. It's an important consideration, not just for reducing costs, but also minimizing the environmental impact of AI systems. Now let's look at how computational costs play out in practical applications. Startups and small enterprises. So for these organizations, cost-effective solutions like smaller models or pre-trained frameworks are essential for them to stay competitive without incurring high expenses. Large enterprises and research and development, these are bigger companies, and they often have the resources to train and deploy large models. And that allows them to tackle more complex tasks like advanced analytics or predictive modeling. Academic research, so universities and research labs, must balance computational costs with the need for cutting-edge results. So they often rely on shared resources or grants. And the public sector, so governments and public organizations, they often face budget constraints as well, making it crucial to optimize computational resources for projects like natural disaster prediction or public policy planning.